look at a few more molecules. We'll start with carbon tetrafluoride. If we draw the Lewis structure for that, we're going to get 4 carbons, or 4 fluorines, symmetrically distributed around the carbon center in a tetrahedral shape. Now in this case, I'm going to leave off all those lone pairs on the fluorine because it kind of messes up being able to see what's going on with the electrons being pulled away from the carbon. In all cases, the electrons are going to be attracted towards the fluorine atoms. And notice that the electrons are being equally pulled away from the carbon center. So what is happening here again is the polar bonds cancel. This is a symmetrical molecule. So since it's symmetrical, it is nonpolar. Now let's take a look at CH2F2. We can draw this molecule so that it looks like this. And if we track what's happening with the electron density, it looks like these two electron density, the directions they're being pulled, cancel each other out. But don't let drawings in 2 dimensions fool you. Remember, this is a tetrahedral structure. So we can just as well draw it if we turn it in 3 dimensions so that it looks like this. In which case you can see that the electrons are being, the density is being withdrawn towards one side of the atom. So in this region here we have a partial negative charge, which means over here we have to have a partial negative charge, partial positive charge. So what we have here in reality is a lopsided molecule. And if it's lopsided, that means it's going to be polar. Let me try with drawing this again here so you can see a little more clearly what I mean. Remember, this is a tetrahedron, so there's our central atom. There's one atom, another atom. Now we're going to draw the 2 fluorines. I'm going to make those green. So there's a fluorine, and there's a fluorine. And they're at the 4 corners of the tetrahedron. You can see that this side of the tetrahedron is going to be partially negative. This side is going to be partially positive. Let's try ammonia now. And the Lewis structure for ammonia looks like this. We have one lone pair. If we have a lone pair on a central atom, that means the thing is lopsided. We know it has to be a polar molecule. The same thing if we have nitrogen trichloride. Even though nitrogen and chlorine have the same electronegativity, and so these bonds are not polar, the problem is you've got a lone pair up here. And remember, this lone pair is going to be a more negatively charged region. So once again, that lone pair is going to make things lopsided. So if it's lopsided, it's polar. Let's do one more. Water. This is one of the most, actually I would argue it is the most important molecule on the planet. Without it, we do not survive very long at all. If I draw water like this, a lot of you will still look at it and say, hey, that's linear. No, it's not linear. Remember, this is bent triatomic because these lone pairs occupy space. So really we should be drawing water as looking like this, with the two lone pairs bending the hydrogens towards each other. In terms of what is going on with the electrons, we know we've already got electron density up here because we have the lone pairs, and additionally the electron density from the hydrogens are being drawn towards the oxygen. So this is very definitely a polar molecule, with the negative end kind of on this side and the positive pole on this side. So water is very definitely a polar molecule.